All right, I think let's get started. So my name is Bryce Adelstein-Lelbach. I work at Lawrence Berkeley National Lab, which is a DOE laboratory in Berkeley, California. I'm in the computer architecture group there. I also work with a numerical algorithms group. So I spend about 50% of my time working on parallel runtime systems, and then I spend about 50% of my time trying to convince scientists to use those parallel runtime systems in their application codes. Most of what I'm doing right now in terms of application work is global climate simulations. So looking at predicting weather trends many years into the future. So this talk kind of started 2 to 3 years ago when I was at Louisiana State University. And I was there for about 5 years working with Hartmut Kaiser, who's the chief architect of the HPX runtime system. And I did a lot of work on the thread scheduler while I was there. And at some point, Hartmut was like, we should benchmark this thing. And me and this PhD student named Patricia got started on benchmarking that thing. And we got some initial results, and we brought them to Patricia's advisor. And she looked at the results, and she's like, I'm not going to even spend time talking about these. This has no meaning at all to me. Go try again. And then it was because the results that we showed her were basically just lines on a graph. And she was like, I have no idea what's going on here. You've just shown me a line. Is this an average? Did you take one sample? What's your variance? This has no meaning. And as it turned out, as we started doing our benchmarking for a lot of these small overheads we were measuring, we realized that a lot of the stuff we were initially doing was just completely garbage. So this talk is sort of a best practices talk about all of the stumbling that me and some of my colleagues did to come up with methodologies for benchmarking our code in a way that was statistically sound and getting results that we actually believe or kind of believe in most of the cases. So I'm going to start by talking about why I think performance and performance problems are really difficult. So let's start by talking about not performance problems. So you have some problem in your code that's something that shows up in serial, like your code seg faults. It's not a race condition. That we have an iterative process that we can go through to solve this problem. We'll easily know when we're done with that process because we can get a yes or no answer. It's not a race condition. It's something where if the test doesn't seg fault, you're done. It's nice and simple. Sorry, I'm going to move this mic down a little bit. So the process is you start off with you're doing some analysis with some debugger or some tools to try to figure out what's the source of the problem, why do you have this seg fault. You go and apply some fix, then you go and you build and test and determine if it's solved or not, and if not, you lather, rinse, and repeat. And you do this until the problem goes away. With performance problems, it's much more difficult because the only step that you really sort of know what to do is I've got some fix that I'm going to try and put it into the code. You don't really have a good way to test because most of your performance problems you're not going to get a yes or no answer out of. You also don't always have so easy of a way to analyze the code, but let's focus on the testing for right now. So performance is not a Boolean quality. Your code is not either slow or fast. Your code may be slow, but it's never going to really ever be fast. It's going to be somewhere on this scale. It may eventually reach a point where it's fast enough or where it's not slow enough, but it's not something where you're going to get a clear answer unless you formulate one. And you never really stop optimizing unless you set some metric for yourself to stop optimizing. And that's one of the problems. Performance data is also subject to random error due to the natural variability and variance on our computer systems. And that becomes a big issue because even if you sort of have what you think is a good test, like let's say you need something to take less than, 100 nanoseconds, then there's the question of how do you know whether or not you've actually achieved your goal? You may get a result that says, hey, it looks like I have, but you don't always have confidence that you've actually achieved that result in production and that that's the real performance. So first, let's talk about how we define performance. So again, there's not fast, but there's fast enough. You need to come up with metrics of some sort. One of the metrics that my community frequently talks about is some sort of real-world performance metric. So like you want to be able to do a certain number of simulation years per day. So the sort of scientists I work with, they don't care about flops or sort of roofline performance. All they care about is we want to be able to get a certain amount of the simulation done per day. That's our requirement. We don't care if it's only using 5% of the compute resources in terms of efficiency. If it's only 5% efficient, that doesn't matter, as long as we're getting sort of the performance that we need. People like me care more about roofline performance because we don't want scientists running code that are only utilizing 5% of the machine, but are actually using the entire machine. Some people may care about deadlines. I think that's a lot more sort of out of the HPC industry. You may need certain stuff to take a certain period of time, and if it takes longer, then that's not acceptable. And you need to be able to come up with meaningful definitions for performance in your code, and then you need to be able to come up with meaningful metrics for how you measure that. So now this is going back to the sort of idea that computers have error, that there's going to be variance in the performance. So there's two sort of types of observational error. An observational error is the difference between what you measure and the true result. The first is random error. So random error are errors that are caused by natural variance. You can't do a lot about that other than account for it. Systemic error is usually something where you screwed up in your experiment design. Sometimes it's something where you didn't necessarily screw up, but it's something that just happened in your experiment design, and you can correct for it. Usually systemic errors are caused by some inaccuracy. They may be constant or proportional to the true result and can be corrected for. But observational error is unavoidable because random error is unavoidable. Meaningful performance analysis must account for error, which means that you have to use statistics. So variance on computer systems is a reality. You can reproduce bit for bit results in terms of the quality of the result. You can run something 100 times and get the same answer bit for bit. But you can't reproduce the performance of each of those runs. Each one of those 100 runs will have a different performance profile. It may be very, very small in terms of the difference, but it'll always be different. Every time you re-execute your code, you're adding a new sample to the population of the population being the true performance of your code. The population is infinite. It's never going to do the same thing, the same exact thing each time. So there's a number of reasons why this happens. A number of them are hardware related, so there's hardware jitter. The pipeline fill level will have an effect on the execution time for one instruction, and that's going to vary. There's a difference between the CPU and memory bus clock cycles. That means sometimes your CPU has to wait for the synchronization of memory accesses. That's going to vary from program execution to program execution. These days, CPUs, at least in HPC, are more and more moving towards frequency scaling for power management reasons. So your compute resources may have heterogeneities in processing power to fulfill some power budget. Shared hardware caches obviously are going to cause variance because they're shared between multiple different cores and threads and maybe even other processes. Larger memory segments may have variance in access due to the actual physical distance from the CPU. And there's a whole long list of things that the OS can do to screw with your program and introduce variance. I've just picked 2 of them, but there's probably about 100. Some hardware interrupts require the OS to handle them immediately after delivery. That can cause a problem. Migration of non-pinned processes can really screw with your program. One of the reasons why we frequently care about pinning processes in HPC. And also, you've got the observer effect, which is more of a systemic error. So the observer effect is the principle that anytime you instrument something, you're going to change the result. This is especially true in our industry. If you have some piece of code that you think has a performance problem, and you go and add an instrumentation, that instrumentation normally adds overhead. So then when you go and look at the results, you were looking at not just, you thought the code was slow to start with, and you went and made it slower so that you could see how slow it was. So you've added some bias just by the practice of instrumenting it. So this is what variance looks like on large HPC systems. So on the bottom here is just the processor. My laser pointer seems to not be doing so well. On the bottom here, there's the processor number. And then on the y-axis, we've got the runtime. And for each one of the processors, it's just a range of the variance for the different runs that this test was executed on. And you can see that there's some real odd ones here where there was some substantial system noise at large scale. But even for the ones where there's not real outliers, there's a good bit of noise. So some of these systems are less noisy than others. One system that's really known to be very noisy is a Ivy Bridge-based cluster at LBL called Edison. Blue Gene Q systems are generally pretty quiet, but they all have noise. And the noise really hits you, and it really hits you at large scale, but also even just on one node, you still will hit noise. All right, so now we're going to sort of get into what I'm going to call statistical best practices. First, let's define statistics. So statistics are a really good way to lie to yourself. It's really true. Statistics is an interesting field of mathematics because there's often not a right answer. There's usually, you have many different sort of approaches that you can take. And so because of that, it's very easy to take the wrong approach or to use a method and then to misinterpret it, because there's a lot of stuff in statistics where it's somewhat open to interpretation. It's not like some other fields of math where you can really sort of have this is how you solve this problem, you solve it and you get an answer. So I have another definition, which is that statistics is a good way to extract conclusions from your data. One of the problems that we often suffer from in performance analysis is that we have too much data. You really run into this if you go into your benchmarking with no idea of what you're collecting, and you just say, I'll just collect all the data. I'll just get all of it, because more data is good, right? And then you have all this information, and you have no idea what to do with it. And statistics are a good way to sort of work your data set down to something that's meaningful. What statistics actually is the science of data collection, analysis, interpretation, and presentation. Before we had sort of big data and data science, statistics was the science of data. So let's start off. I'm going to show you guys just a case study. So this is for some science code. It's a computational fluid dynamics code that runs on an adaptive mesh. And this is the sort of graph similar to what I showed that advisor of my PhD colleague, and she would have just said, no, go away. This is not good. So the problem with this is we've got a graph, we've got some scaling curve, and we've got some points here, but we don't know anything about what these points mean. Have we collected one sample? Well, if we've just collected one sample for each one of these points, that's bad because, as we discussed, there's variance and noise on computer systems. And if this is an average, then that's a little bit better, but we have no idea of what the variance is. If the variance is large enough that all of these points could effectively be within the same range of each other. So what we really want to see is something like this, where we've got some measure or some estimation of the uncertainty. So normally you do this by taking a sample standard deviation of the set of data points. So now that we have this information, we can draw some conclusions about this that we wouldn't have been able to see previously. So if you look at this graph right here, you see, oh, hey, the code continues scaling up to 1,000 cores. Maybe you draw the conclusion, well, we can go and maybe now start trying to scale up on a larger system, and go to 2,000 cores or 4,000 cores. But once you look at the uncertainty ranges, you see that that's not really the case. So from 256 to 512, the range of uncertainties don't overlap. We can say pretty definitively that the 512 core count achieves a higher speed up than the 256 core count. Same thing for 768 versus 512. The range of uncertainties don't overlap. It looks like it's probably the case that we get a higher speed up with 768 than 512. Comparing 768 to 1,000, we can see that there's substantial overlap in the range of variance between these two. So the average for the 1,000 core count is higher, but we can't really say that we've really achieved a speed up here, because we could potentially have this case. So this third line here is something that fits within the range of variance that we measured, where it could be that the true performance for 700 cores is actually a little bit higher than what we measured, and the true performance for 1,000 cores could be a little bit lower. And it could be different in such a way that it would change the entire nature of this curve. So what this data tells us is that we need to go back and we need to collect more samples or change the experiment or improve the code so that we get results with less variance, so that we can really distinctively say that those 2 points are distinct, or that we're really scaling up to 1,000 cores. So this is sort of just an example of why I think this sort of stuff matters. If you have you could have something that you're benchmarking where you have huge variances. If your variances are on the order of magnitude with the average that you've got, then your data could be complete garbage. And if you are only looking at averages, you'll never know. All right, so this is sort of the process, the statistical process I like to use in computer performance benchmarking. I don't generally take a null hypothesis approach. If anybody here is a statistician and wants to argue over that with me later, we can do that. But for now, let's just assume that this is a good process. We're going to form a hypothesis. How do we expect performance to change? Then we're going to come up with a test to determine if we were right, gather data, statistically analyze it, and draw conclusions. So let's talk a little bit more about how we're going to come up with that test. So the first thing I suggest you do is you identify what your variables are. So your variables are the knobs you're turning or the things that you're measuring. Classify them into independent, dependent, and control variables, and then make sure to express that information as metadata in your data set. The reason that that's useful is if you start needing to do exploratory runs, so like let's say that you see some weird effects and you're like, all right, well what happens if we start changing these two independent variables at the same time and we do some sweeps to explore the problem space? Then you end up with this really huge data set, and if you have this information annotated, you can write some scripts that will go through and say, okay, well, I know that this is the set of independent variables, so I know how to figure out which data set this point belongs to, because the key in like our little table of data sets, the key is going to be the set of independent variables that are different from all the other data sets. So this makes it easier to organize and manage your data. You'll want to determine what the metrics are that you'll want to use. Normally, once you start getting into some more advanced, if you're not just looking at scaling, if you're looking at some other maybe non-time-based benchmarks, you may end up with metrics that are derived from a bunch of other data. And you want to consider the assumptions you're making. I'm going to say that there's two that we're going to make for pretty much all these slides and that you can usually safely make. Those two assumptions are that usually the sort of stuff that you're measuring is going to be independent, so there's not going to be a correlation between variables. And we're going to also assume a normal distribution. Usually when you're looking at something that's affected by variance in a computer system, it almost always falls into a normal distribution. If it doesn't, it's usually because you've got some other problem. But if you're just looking at, if you're doing everything right and you're just measuring some event and you're measuring the same event every time, the variance will normally fall into a normal distribution. I know, I've done a lot of testing of that. From what I've seen, that's the case. So the first step, sort of at the lowest level of how you start gathering this data, is that you want to determine whether or not you need to amortize whatever you're measuring. If you've got some really small events, you don't want to instrument the events individually, because if you do that, then you'll add massive overheads from the instrumentation. What I mean by this is basically if you've got some for loop, maybe you say, okay, we'll time this for loop, it's got n iterations, we'll divide the time by n, and we'll call that the time per iteration. And what we do is, I like to treat this just as one sample and not try to estimate or come up with some metric for the variance between those iterations, because there's no real good way to do that. So you just treat this as one sample, and then you collect a bunch of samples like these, and you measure the variance between them, and then you move on. So the next step up after that is you do your sampling. So sampling, each independent measure we take is a sample. The samples are meant to be representative of a population, which is meant to be the true performance. And our goal is to gather enough samples to gather samples in sufficient quality and quantity to be representative of the population. It's crucial that you both sample within one execution of the test and across multiple executions of the test. If your benchmark is something that you run once, even if it's doing multiple samples, you're not getting an accurate representation of system noise. Mostly that's because of OS effects that you may not see unless you're running your actual benchmark multiple times. Which brings me to the point of running hot versus running cold. So frequently we need to make sure that the thing that we're measuring is running hot. And by that I mean we want to do some sort of warm-up to ensure that the first few iterations of what we're measuring are not going to have really bad performance because of I/O that needs to be done, or because stuff's not in the cache yet, or because the branch predictor hasn't picked up on something yet. And what you really want is you want to ensure that everything's running hot, because then you know that everything's going to have basically the same performance. The way that you do this is that you're going to discard the first few executions of your test if you're doing I/O, or the first few iterations within each individual execution. I was talking to some LLVM guys, and they were telling me that they're not happy with the way that their benchmarking framework works because when it goes through and it does multiple samples of the tests, but it goes and does run test A, run test B, run test C, run test D, instead of going run test A, run test A, run test A, run test A. And what it really should do is run test A 5 times, discard those, then run the rest of them. When you're discarding data in this way, of course, you want to do it in a uniform fashion. If you just go through afterwards and just say, I don't like this point, that's not really a legitimate process. But if you know that the first few points are going to be slower because of these effects, then you just pick a size and you throw out that first chunk of data. All right, so now we'll talk about how we estimate variance. We do that by measuring uncertainty in some way. So uncertainty is a representation of the amount of error in a certain measurement. There's 2 types of uncertainty. There's instrument uncertainty, which is the inherent amount of uncertainty in some tool. So like if you think about a ruler, if a ruler has a precision of like a centimeter, that means that when you're measuring something, you go and write it down, it's 12 centimeters. But it could be 11.5 centimeters, or it could be like 12.5 centimeters. So the instrument uncertainty you normally say is going to be half of the unit of measurement. If your clock ticks in microseconds, for example, then the instrument uncertainty would be plus or minus 500 nanoseconds. Now this is something that you normally don't account for because normally you're taking a lot of samples and you get an estimation of the variance between samples, but it's something to be aware of. Especially when you're dealing with clocks, it's good to know what the instrument uncertainty of your clock is going to be. So when you've got a set of average data, the way that you get an estimation of the variance is you can take the sample standard deviation of the set. And this is a frequently used method for estimating the uncertainty. There's other methods. This is a good one, especially for normally distributed data. When dealing with derived metrics that used average data, which is what we frequently do, especially when we're looking at hardware performance counters, you can formulate derived uncertainties based on the uncertainties of the average data. So that's what this slide is for, and I have this in here because this is something that not a lot of people think to do, but it's really useful. And also this math is not always easy to find. But so if you have ever got something where you need to go and do something like scaling data, so scaling data, how do we get this number? Well, we take the smallest core count wall time, and then we take, for each of the other points, we take their wall time, and we have some formula that gives us out the speed up. But there's 2 different averaged variables going into that formula. Both of them have uncertainty. So if you look at what the wall time is, you can see that clearly we need to adjust this uncertainty data to be able to get it here. And that's what this math is for, to be able to propagate that uncertainty information. If it becomes really important, I mean, it's pretty straightforward stuff. Again, there's some assumptions here that you're assuming that the variables are uncorrelated, and there's some extra terms if they're not. So that's what those slides are for. All right, next I'm going to talk about Boost.Accumulators. And my initial intention was to tell you guys all how great Boost.Accumulators was, but then I ran into a fun problem with Boost.Accumulators. So now I'm going to beat up on it a little bit. So this is from Boris's book. His like one line, little thing of what Boost.Accumulators is that it's a good library for getting things like the mean or the standard deviation. So my first issue with Boost.Accumulators is they don't actually define a tag for standard deviation. So that's not that bad, right? They give you variance. So you go and you create some accumulator set. This is going to be some data structure that will maintain running numbers for whatever statistics you want. You go and push data into it. And then at the end, you go and get the data out. Well, they don't have that tag for standard deviation, but we know that standard deviation is the square root of variance. So we just take the square root of variance, and we have the standard deviation, right? Does anybody see a problem with this? What? I'm sorry, I still can't.
The answers inequality, so the estimator of the square root is not the square root of the estimator.
Yes, that's one problem. I was more so thinking of what standard deviation are we calculating here?
It's an online estimator, so it's an approximation.
So more so what I'm asking is, so there's not just one formulation of standard deviation. There's a few of them. So this question, and I'm now going to beat up on Marshall, who is not here to defend himself because he's giving a talk, but this was a question that came to the Boost mailing list in 2012. This guy was asking, how do I calculate the sample standard deviation over a stood vector of doubles with Boost accumulators? And Marshall gave the answer, well, do this, which is the thing I just showed you, which would work, except that he wants the sample standard deviation. So as this guy points out, the problem is that that's the population standard deviation. So it's where you have variance divided by n. And what he wants is the sample standard deviation, where variance is divided by n minus 1. So there's a number of forms of this, but the first form here, the uncorrected form, which is the form where degrees of freedom is equal to 0, you've got a 1 divided by n term, so the variance is being divided by n. This is taking the standard deviation of an entire population. That's a valid thing if you've got data on the whole population, but the more frequently used form is the second form, which is the sample standard deviation, where you've got a n minus 1 term. So if you go into Excel and you plug in standard deviation, it gives you the second form. And it's a little odd that Boost.Accumulators doesn't do that. What you get with Boost.Accumulators, if you just go and do the square root of the variance, is you get the first form. And if I looked at some other frameworks that do statistics, so NumPy does the smart thing, which is NumPy has a function called standard deviation, and you can tell it the degrees of freedom. The default behavior is to do the same thing as Boost.Accumulators, but it gives you an easy option to not do that. The actual fix is that you have to add in some term to correct this problem, so you just multiply it by n divided by n minus 1, but this is not something that I think most people are going to think of. And for something that's generally, this is the standard definition of standard deviation. This is sort of the one that everybody uses. And the fact that there's not A, a tag for this in Boost.Accumulators, or B, like a nice easy way to get this, or any documentation on it, is a little bit difficult. Other than this, Boost.Accumulators is a really good statistical framework. I do take issue with this. I'm hoping maybe I can talk to the maintainer and try to get a standard deviation tag added and have it be like the moment tag where it's a template and you can specify the degrees of freedom as a non-type template parameter. So, all right, just reviewing a little bit of what we went over. So, for the lowest level, I want you to take individual measurements in your code and use amortization if relevant, if the stuff you're measuring is really small. Then accumulate multiple measurements and uncertainty estimates in the code, and then output that in some way. Gather results from multiple executions of the tests, and then recompute your uncertainty estimations. So this is, again, just for reference, this is the math for combining two data sets that you've got two sample standard deviations for a data set, and you want to get the combined sample standard deviation. I know this is unpleasant to look at, and don't use this for population standard deviation, because it won't do what you want. But this is the math. If you ever need it, you know where to find it. It's here in this slide. All right, so once you have this, then you've got a data set where you have an average data over multiple executions, and you have some uncertainty. What do we do with that then? Well, we're going to construct what's called a confidence interval. So a confidence interval is a way to describe the amount of uncertainty associated with the sample of a population. It's constructed from 3 pieces of information: an uncertain confidence level, statistical data, so that's some average value in the sample size, and uncertainty for the data. Confidence levels, there's a whole number of them you can use, and there's some standard ones that are used because you used to have to look them up in a table before computers were, a thing. Usually I use a 95% confidence level for doing computer performance benchmarking. That's a pretty good metric. Social sciences may use a higher confidence level, but that's a pretty good one for the sort of stuff that you do when you're benchmarking computer performance. And then you plug it into this formula here, so you multiply this value called the critical value by the uncertainty, and you divide it by the square root of the sample size. So one of the important things to note is that the confidence interval is a measure. It's sort of like uncertainty, where it's going to give you a plus or minus to your average, but it's nice in that it gives a representation. It has data from the number of samples that's going to get onto your graph. That's one of the reasons why I like confidence intervals, is that then when you look at a graph with confidence intervals, you've got a lot of data. You've got data about the uncertainty, you've got data about the sample size, you've got data about the average. This z-value, that last point there, is just how do you find out that z-value. If you've got a small sample size, you go and do a student's t-inverse cumulative distribution function with the cumulative probability of 1 minus r, and then with the degrees of freedom of n minus 1. And if you plug that into Excel, it'll give you the answer. It's just called t-inverse, t-I-N-V. For larger sample sizes, you can use a lookup table, but in CS, we never really take sample sizes large enough to safely use it in a lookup table. Yeah?
I think we can avoid Excel, hopefully, because Boost math also has probability distributions and it has quantiles.
Oh, I guess that's a good point, and given that I do a lot of Boost stuff, I probably should have thought of that. So yes, don't use Excel for this, use Boost math. That is the correct answer. Boy, I probably should have come up with that one. One of the useful things you can do with confidence intervals is determine the correct sample size based on an initial pilot set of samples. So given a margin of error, usually you just use 5%. I've never used anything but 5%. A critical value, the uncertainty, and a mean, you can determine a sample size so that you can get the confidence level you want at the margin of error that you've requested. If this calculation gives you a really unreasonably large sample size, it probably means there's a problem with your experiment. Generally, the sample size gets much larger if the relative uncertainty is really huge. So confidence intervals are something that get frequently misinterpreted, but what they end up meaning is a confidence interval tells you that if the true performance lies outside of, say, the 95% confidence interval, then an event occurred which had a probability of 5% or less of happening. So a 95% confidence interval does not mean that 95% of the data lies within the interval, and a confidence interval isn't a range of plausible values for a sample mean. You can interpret it as an estimation of the plausible values for the population. That's what we want. We want an estimation of what the plausible range of performance is for the true performance that you're trying to study. So on a normal distribution, this is, I don't know why I didn't have that be 95, but the confidence interval will cover from a lower limit to an upper limit of the range of values of the population. All right, so I'm going to talk about another case study. This is a performance benchmark for HPX's context switching routine, which is about 25 lines of inline assembly code, and that code's responsibility is to context switch from one user space thread to another. It tends to have very microarchitecture specific performance because it relies heavily on the branch predictor being able to figure out what you're doing. The context switching like that is not something that you normally do in your code, so it's not something that the branch predictor is always great about figuring out. You have to sort of prefetch and pray. So the benchmark, we run it with a large number of iterations for each execution, like 100,000. And then we set a number of contexts. The reason that we could just say, hey, just reuse this one context each time, but in the actual HPX runtime, you won't be able to reuse the contexts because they might be suspended waiting on data. So we just have a pool of contexts that we use to create an artificial poor caching behavior that mimics what we actually see in the production code. So the more context you have, the worse the caching is going to get, and the worse the TLB performance is going to get. So this is looking at with a 95% confidence interval. And this looks good, but we started noticing there was some weird, we noticed some weirdness in the data set, and we weren't happy with it. One of the things we didn't like was that even though we had taken a large number of samples, I think we took like at least 100, maybe 200 separate executions of this on a large HPC system. And we tried it on different nodes because we thought maybe just the node was weird. It wasn't that. But so these were the uncertainties. They were a little bit larger than we thought they should be, especially for how the confidence interval looks. So we really felt like something was up. So what we decided to do was we started looking at our assumptions as to, well, what could possibly be wrong here? So the thing I decided to do was to do a normality test. So a normality test is some method to determine whether a data set fits a normal distribution. As I said before, if you've just got normal variance effects in your data set, it should be a normal distribution. So there's a number of different ways of doing a normality test. There's rigorous methods, there's graphical methods. I kind of just used an informal method. This isn't a way that this wouldn't tell me whether it fit a normal distribution or not, but if it didn't fit a normal distribution, it would definitely tell me that. So in a normal distribution, the mean and median should be the same. So what this little test I came up with was just take the difference between the two and then divide it by the maximum of the two so that you get the relative difference between the mean and the median. And then if that number is anywhere near the order of magnitude of like 1%, then you've got a problem because that means that the difference between the two is not really, really small. So this is the result that we got. So this has got a reference platform here. We run this benchmark on a bunch of architectures. So the reference platform is the points at the bottom, and that's on an Ivy bridge. And we ran this on older platforms too, thinking that maybe it was the newer platforms, we didn't get this weird effect, and the older platforms, We did, but no, it was just this one Sandy Bridge chip. And so what we see here is the Ivy Bridge, it looks like there's no indication that the data doesn't fit into a normal distribution. It's very, very small relative difference between the mean and the mean and the median. For the Sandy Bridge data, though, it's very clear that it doesn't fit a normal distribution. The mean and the median are way too different. So finally, I had the brilliant idea to actually look at the data in a scatter plot, and we saw this. So this is not good. So we can see there's clearly two peaks here. So there's a low peak and there's a high peak. And as it turned out, about half of the data points were at the sort of low performance and half were at the high performance. And my first reaction was, well, it must be that like some of those are running cold, that like I didn't discard enough data points at first, but no, that wasn't the case. We looked at the order that the data was coming in, and we could tell that this was just completely random. We still haven't figured out what's going on here. But if you separate these data sets, they both fit a normal distribution. What I can tell you is that we thought we were measuring one event n times. We were actually measuring two distinct events, n divided by 2 times. There's some sort of race condition or some sort of problem in the code. We're beginning to suspect that this is probably a bug in the benchmark as opposed to a bug in the context switching routine. It took us like 3 months to figure this out. I don't think we would have figured this out if we weren't so concerned about following a rigorous statistical process. It was unlikely that we were going to ever pick this up from looking at the actual data set because it was really hard to tell that there was nothing in between these two regions here. If you looked at the data set, because of the randomness, you had to be looking for this if you were looking at the raw values to be able to tell that this is what it looked like. All right, so now I'm going to talk about sort of methodologies for data collection a little bit. And sort of what your options are on x86 platforms. Some of this stuff is going to be a little bit specific to x86 platforms, but that's what I know, so that's what we're going to talk about. So we'll first start by talking about time-based. How much time do I have left? Okay, cool. So first we'll start by talking about time-based benchmarking. So there's a few different clock sources that you have as an option on an x86 CPU. So you have a system-wide high-resolution clock. That's going to be monotonic, frequency stable, higher latency and overhead. Resolution is going to be in nanoseconds. Your tick time is going to be more than that. It's going to really depend, but it'll be slightly larger than that. Times can be should be able to be passed between threads. This is not something that's a thread-specific clock like some of the hardware clocks. On Linux, you access this with clock get time, reading clock monotonic. On Windows, you get through this through query performance counter or query performance frequency, or you just use chrono, which is the correct answer. This is suitable for measuring most events, which are microsecond and up in terms of durations. If you're trying to measure stuff in the nanosecond or cycles range, I would not use this clock. I would either amortize it or use this clock. This is the timestamp counter clock. There's actually a few different ways of getting a clock that has these properties. You can get it through the timestamp counter, or you can get it through one of the Intel performance events, one of the Intel hardware performance events. I've tested both of them, and they really both have the same performance profile. It's just a matter of what instructions you're using to get at them. So the TSC type of clock, it's monotonic, it's lower latency and overhead. It's not really frequency stable. In some microarchitectures, and in some it is. The resolution is in CPU cycles with caveats, and the tick is in base clock cycles these days. So it used to be that that the frequency that this ticked at changed when your CPU frequency changed, which meant that it was really good at giving you an accurate representation of the number of cycles executed, but it was very bad at giving you an accurate wall time because you had no way of knowing what frequency to multiply it by, because the frequency would change during the course of whatever time you were measuring. So a few years ago, about 4 or 5 years ago, Intel and AMD added support for a constant TSC frequency, which is present on pretty much every x86 chip these days. And what this means is that previously it was good at measuring cycles and bad at measuring time. Now it's good at measuring time and bad at measuring cycles because it doesn't actually reflect how many cycles were executed. It just always gives you a count that cycles at a maximum CPU frequency. So if your CPU was time scaled, was frequency scaled, it's not going to be an accurate representation of the number of cycles executed. It usually ticks at around at 100 or 133 megahertz, depending on your microarchitecture. There's assembly instructions for getting to this. The cycle counts are thread specific. And the only reason to really use this is if you want to measure something at the cycles or like nanoseconds range. And I don't remember where it'll overflow, but it depends on your processor, obviously. But don't use this for measuring something that's going to take like a day. It's a bad idea. You should usually just use Chrono. Chrono is the correct solution unless you need to measure cycles or nanoseconds. Chrono is the C++11 standard facilities for manipulating dates and times. There's basically 3 types in the libraries: durations, which is a span of time; time point, which is a duration that's passed since the epoch of a specific clock; and then you have clocks, which are objects with a starting point and a tick rate, and they can be queried for the current time. So there's 3 different types of clocks on most of the major platforms that I know of. At least on Linux, these are all type-def together, so the distinction doesn't really matter. I'm not sure what's the deal on Windows, but I know at least 1 or 2 of these are type-def together. But in theory, the idea is that the system clock is a clock that may not be monotonic, but represents the real-time clock, so the real-world time, and could potentially be adjusted by the user. The steady clock is a monotonic clock that will never be adjusted. And high-resolution clock will always be the clock with the shortest tick period. In practice, these days, in most platforms, these are all the same clock. All right, so this is the little wrapper around Chrono that I usually use, and I just drag around from code base to code base. I just threw it in here because I used it in so many places I figured somebody else might find it's useful. So it's just an object that when you create it, it takes a timestamp using Chrono, and whenever you call elapsed, it gives you a time in seconds from when you created it, and you can call restart if you want to restart the timing. It's just a nice little simple object. This is the only thing I use really for measuring stuff in terms of time. All right, so now we'll talk about other forms of performance data that you might care about. So memory benchmarking's sort of the next obvious thing you might want to look at. So there's a few different approaches here. First, you want to figure out what you're looking at. You may care about how many objects you've allocated or deallocated. That's really more so looking at the overhead of your memory allocator. If you're allocating tons and tons of small objects, and if you're doing it in parallel, that's going to have a substantial performance impact depending on the memory allocator that you've got under the hood. You may also care about actual memory. So in that case, you have to figure out what specifically you're looking at. Are you looking at your whole program? Do you want to just look at it per object size? There's a lot of great external tools for looking at this. I tend to use Google Perf Tools a lot because I use it as a memory allocator anyways, so I just sort of get it for free. And Google Perf Tools has this heap checker, which will basically give you a sort of a per class or a per function overview of who allocated what memory. And tcmalloc has built-in support for giving you a sort of a coarser snapshot where it'll tell you how many objects of a certain size have been allocated and how many allocations have been done by a particular thread in your program. You can also, if you want to do it yourself, you can just overload operator new and delete. This is pretty straightforward. You just use some static or you use a thread local storage because you want to try to reduce the cost of your instrumentation. You can just go, if it's in parallel, you just go and gather stuff from the thread local storage when the program is done. And you get the size, you figure out how many objects that amounts to, you store it, and then you call the actual operators. So this is pretty straightforward. All right, now we'll talk about counting copies and moves. So this came up when we were first porting HPX to C++11 and to move semantics. And we wanted to make sure that we got move semantics right. Because we knew that there were a ton of places where we were copying stuff that we shouldn't be. This really happened because HPX is an asynchronous programming framework, and there's a lot of places where we make design trade-offs between duplicating data and not duplicating data, because duplicating data lets us expose more asynchrony. But it became a problem because our initial implementation of async would copy the arguments 6 times before it got executed. It should only have to duplicate them once. So we just created some mock objects, and we wrote a benchmark, and we ran the benchmark, and we saw what numbers came out, and we fixed the code until we got the numbers we thought we were right, and then we turned it into a unit test so that if we ever broke the code, we'd know. So this is something I suggest that anybody who's got a C++11 code base with move semantics in your interface, You should probably do something like this. You're probably making assumptions about, how is data being passed around through your libraries. Why not do this? This is something that's really easy to write a unit test for. This is one of the few yes or no answers you'll get. Okay, so the next couple slides, I'm going to plug in some cool Intel software. So x86 processors have a diverse set of performance counters. The pros of the performance counters is that they're low overhead, they're very diverse and descriptive. The cons is that they're super microarchitecture specific. What I mean by that is if you go from Sandy Bridge to Ivy Bridge, which are the tick and tock of an Intel development chain, the counters will be different. The counters, some of them are estimations, some of them have some inaccuracies. They actually pulled the flops counters from Haswell because they had historically overcounted by many orders of magnitude and were very, very much so not doing at all what you wanted. Hopefully they'll add them back in later. But a lot of these are sort of estimations. You have to be careful with some of them. And the real problem is that you used to really need needed to have a very specific specialized knowledge of how to read these counters, how to interpret them, what was the math that you were going to do once you got all the raw data. Fortunately, there's a really cool tool now that has all this knowledge baked in, so you just have to develop institutional knowledge with the tool, and then your code will be faster. So there's low-level frameworks for getting to these counters. Don't use them. Use Intel Amplifier. So these are the low-level frameworks, though, that you can use. There's PAPI, there's the Windows Performance Counter Framework, and I've been told by Apple people that there's this thing called CppC.h. I don't write any code on Mac, but some of my friends who do write code on Mac told me that that's the thing that would be the low-level interface that you'd use. But you shouldn't do that. You should use Intel Amplifier. I don't work for Intel, but I love this product. This is the coolest profiling tool ever. I'm not going to even talk about other profiling tools because that's how good Amplifier is. So Amplifier is a sampling-based profiling tool. It runs your application and collects snapshots of the performance metrics while your program is running. Works on Intel processors. You can assume that from the product brand. It runs on Windows, Linux, Mac, and Android. It's not tied to any particular compiler. You do get slightly more information if you use the Intel compiler, but it works with all the major compilers. It requires no code changes to use because it's sampling-based. It gets data from multiple data sources, so timers, hardware performance counters, and from OS metrics as well. The performance data can be viewed at a function granularity or at an assembly line or source code line granularity. And it analyzes everything, so it's a full system analyzer. It'll look at kernel calls, subprocesses, threads, etc. It's got built-in analysis passes which derive useful higher-level performance metrics from microarchitecture-specific raw hardware counters. Those built-in passes used to be specific to a particular microarchitecture, but I just got access to Intel 16 this morning, and they've now combined the passes so you don't have to say, I want the memory bandwidth pass for Sandy Bridge. You can just say, go and do the memory bandwidth pass for this microarchitecture. It lets you define your own user. It supports user-defined analysis passes, which is nice. And it's got really great support for instrumenting parallel and distributed code. It has built-in knowledge of OS threading frameworks, OpenMP, MPI, and Intel TBB. So if you go and do an MPI run under Amplifier, it'll know about all the MPI ranks. It'll know about them all in distributed too across multiple nodes. And it's got this interface for parallel programming frameworks to tell Amplifier about their threading constructs, their synchronization primitives, stuff like that. So frameworks like HPX can notify Amplifier about all these things. So it can do really cool things like you can tell it, hey, I want to look at where am I waiting in my code, and it'll go figure out where are you waiting on I/O, where are you waiting on locks, where are you waiting on HPX locks, where are you waiting on some OS call, any place where you're waiting or stuff like that. Let's see, and it's got a really powerful GUI, so that's one of the selling points for me. It's one of the few GUI development tools that I use. I write most of my code in Vim. I'm usually SSH'd into a system and just working after the command line. This is the only GUI tool I use, really. It's standalone on Windows, Linux, and Mac. It also integrates with Visual Studio and Eclipse. I like the Visual Studio integration. It's actually pretty nice. The data can be collected remotely via the command line interface and then fed into the GUI. And it's got a really awesome interface for filtering data. I'm going to show you guys that in a minute. And it has all those built-in passes that I mentioned, and it sort of tells you how to interpret the results. So it almost is kind of like iMovie for performance. So instead of having like tracks of different audio tracks, you've got tracks of your different threads. And what you can do is you can go through and you can edit out, you can like mute those tracks, and you can also like zoom in on a particular region. So this is for one of my sciencey codes where each one of those little black bumps is one time step, and the points in between the little green points where it's not really using the CPU, those are where it's synchronizing between time steps, and then the region at the beginning is the startup costs. And so what I can do is if I don't really care about what's happening at the beginning, so I can just sort of zoom in on the region that I'm particularly interested in. I could even zoom in on those little synchronization regions and just look at what's happening in that period too. And if it's got all these metrics, so these are sort of the high-level metrics for whether it's for if it's got pipeline issues, if it's back-end bound, front-end bound, but you can also expand those out into actual metrics, so your cache miss rates, your TLB miss rates, et cetera. And then if one of these metrics that it has is above a certain threshold, it'll turn red, and you just sort of scroll over it, and it'll tell you what it thinks the problem is, and it'll give you some general advice for like, here's how you could fix this, and it'll tell you like where in the code is the problem. So this thing will tell you like, okay, this is the type of problem that I see, this is the place in your code where I see that type of problem, you can take that information and go try to fix it. So I've taken this tool and sat down with production science code bases that I've never seen before, and in an hour gotten them like 20 or 30% speed up, just going through and finding dumb stuff that they would have never really found otherwise. So I think it's a really, really powerful profiling tool. And I think that, there's maybe one more slide. So this is looking at bandwidth. And this is kind of cool. You can see where you can see the little valleys there are the parts of my code where I'm calling laypack. And the other regions are the parts of my code where I'm either doing data copy, which is the regions where I'm sort of at peak bandwidth, and the ones where I'm sort of middle bandwidth is where I'm in an explicit operator that's bandwidth bound. Oh, and then they've got this. So this is another new cool thing. So this is the Vectorization Advisor. It just came out in the Parallel Studio 2016. And it does the same thing that the other tool does, but just specifically targeted for vectorization. This is really important because if you're doing anything where you're crunching numbers, you're missing out if you're not vectorizing. And it's getting worse. The vector units are going to continue to be where most of your flops are. You need to be able to vectorize your code. So I'm really, really big on this tool. I think if you're writing code on an x86 platform and you care about performance, you're being irresponsible if you're not using this tool. This is a very powerful tool. Intel builds these chips. They know what they're doing. They have a lot of institutional knowledge about how to debug these performance problems, and this is the tool to do it with. So next I'm going to talk about this idea of writing performance tests. And this is one of the things I wanted to really sort of talk about when I proposed this talk. So the idea is that let's try to write unit and regression tests for performance just like we do for correctness. There's a lot of challenges here, but I think it's a doable thing. So you've got the issue of how do you implement automated performance testing that follows some of these like statistical practices. Like your performance testing framework may not be set up right now to run a test 20 times and discard the first 5 runs of that data set. And if your performance tests are stateful, if they rely on like the previous results, you may need your automated framework to store this data. That gets to be complicated. And you need more than just the machinery to run the tests. You may need some sort of automated analysis to generate graphs or something like that. The challenge is really because like when you're automating from the debugging process, you've got some tests, you take it out, you put it into a framework, it's got a yes or no answer. For the optimization process, you kind of got to automate both of these steps. And again, you've got the issue where you don't really have a yes or no answer, so you may not give a test failed or test didn't fail, but test produced a graph. Go take a look at it. So the stateful performance tests are probably what most of your benchmarks are right now, where they output absolute values. To automate these tests, you need some way to compare the performance against a previous performance. So either your automated build system stores that information, or it goes and checks out a previous build and builds it, and then compares the output from the 2 results. So there's some frameworks that do this. Mozilla's been doing this for at least 4 years. They used to do it with BuildBot, but now they do it. They have a new system. So this is just one of their visualizations showing the performance of a particular one of their benchmarks from the past few days from all the commit check-ins. So this is like sort of the thing that I think would be really cool to see more of in the industry. I think this would really help out with keeping performance issues from getting into the code and keeping regressions from happening. The other thing I'm really trying to push is this idea of writing stateless performance tests. So the stateful ones are kind of more challenging because you need to have some context to evaluate them. But if you can come up with a way to have a performance test that gives you a relative value, so you're going to compare two different things in the unit test, then you can kind of get a yes or no answer. So some of the examples I've come up with is like, if you've replaced a lock-based queue in your code with a lock-free queue, write a separate benchmark that benchmarks the performance of the lock-free queue versus the lock-based queue, and then compare those two, the performance from both of them. And if the lock-based queue is actually faster than the lock-free queue, then that's a bug because you just replaced the locked-based queue with the thing that you thought was going to be faster. So there's a bunch of examples of where this can be useful. So if you're recomputing data locally, or if you've got some sort of software cache, the caching or the recomputing locally should give you more of a benefit than the cost of going to some centralized system. Beam is going to talk about, in his talk, Beam, am I pronouncing that right? Bem? He's going to talk about algorithmic complexity testing in his talk, which is tomorrow at 4:45. So you guys should go to that. That's going to be pretty cool. But the basic idea here is whenever you face a design trade-off with performance implications, try to write a stateless test for it and then add it to your automated testing framework. Because a stateless test is something where you should be able to say, yes, this thing that I assumed was faster than this other thing is faster than that, so then the test passes. So you don't have to add any new machinery to write that type of test. So just to summarize some of the things we talked about, so we want to try to take a scientific approach to performance benchmarking, where you've got some hypothesize, design a test, run the test, analyze, draw conclusions. You want to try to manage and test your assumptions about your data, collect a statistically significant quantity of data, measure and propagate error, and develop unit and regression tests for performance. All right, this is where I work. So I think we may have a little time for questions, or you guys can find me offline.
You said that you experience a uniform distribution in general, because that's almost always the case. One thing, there are two parts to this question. The first one, the first part. Hello? What do I need?
Yeah, I can just repeat it, yeah.
Well, the first part to the question has to do with that in a given test, if you repeat a variable with any distribution whatsoever enough times, you get a uniform distribution.
Yes.
On the other hand, if you have a distribution and you're trying to see when you have varying amounts of additional noise, when there's no noise at all, you'll get some base minimum. And then there's an exponential curve out to infinity, depending on how loaded the machine is, for example. So I'm wondering.
Yes.
Okay, so I'm wondering, is it possible, because sometimes what people do is they discard the high and low,
Yeah.
and they take the average of the middle. There's another thought that the low ones are the more relevant, and the higher ones could be more easily discarded. Do you have a thought on that?
So the question is about the practice of sometimes people discard the high and the low and just look at the middle, but there's some thought that maybe it's really relevant to look at the high and the low.
The low in particular is,
Yeah.
is at the hard bottom.
By low, you mean low performance or?
No, I'm sorry, low time.
Yeah, you see the thing about the low and the high. So you can consider the best time to be like your best case scenario,
Right.
And you can consider your low time to be your everything goes wrong scenario. So I think that's a valid thing to do. Yeah, I wouldn't rule that out as a possibility.
Okay, and there's one other part to this thing, which is you said you want to discard the first few runs because the cache isn't warm, that the system is right. Now, what about the other side of the coin, where you don't have the high temporal locality? In fact, we have a particular thing like pop count. But this is just an example, where what you're trying to do is determine the number of 1 bits in an integer. And the fastest algorithm we know when the cache is hot is to look up the answer. Well, when the cache isn't hot, then if there are other things that do the calculation by taking a single word and repeatedly applying a sum of counters so that the instruction stream itself is already in the cache. So the question really comes down to, is it fair to assume that the machine is hot if the thing that you're calling is called not every time right after the other?
So the question is, should you always be looking at just hot cases when sometimes your code is going to be called cold? And the answer is no. So one of the things that I sometimes, my only point is that if you're going to look at, you should either look at hot or cold. Don't get any of the in-between values. If I'm going to try to look at something cold, I'm going to run other stuff in between. Maybe I'll like run it over, I'll just sleep for a period of time. But the only thing that matters is that you don't want to get intermediate values because that'll screw you up. But that's a very relevant. The example he mentioned in particular was doing pop count. So yes. Other questions? Is this mic working or?
It's the same one.
Okay.
Assuming your crazy data from before isn't a benchmark problem,
yeah.
Did you consider fitting the data to a double Gaussian and using the width instead as the error bar?
Yes, we did. It does fit a double Gaussian. The question is about the crazy context switching data that I had before. The question was, did we look at fitting it to a double Gaussian? I'm pretty sure we did. The issue is that it wasn't that we couldn't find a fit for that data. The problem was that we'd like to know why that happens. And we'd like to know why it only happens on one particular chip, and it happens to be the system where we have the fastest clocked processors. So we're really, really interested to know why that happens on a 2.9 gigahertz Sandy Bridge processor, but doesn't happen on the 2.5 gigahertz Ivy Bridge processor, and doesn't happen on the 2.2 gigahertz Westmere processor.
Which is curious, but maybe the distribution just is double Gaussian.
Yeah, but I can't accept that it's just double Gaussian for one particular microarchitecture.
It sounds more likely to me.
It may be, but one day I'll figure this out. It's a really weird problem. I'm inclined to believe that I've done something wrong.
Well, I'm just saying this because a friend of mine recently was trying to fit a Gaussian to physics data, and then somebody said, try double Gaussian and it fit.
Yeah,
and he doesn't know.
The comment was that he had a friend who had had a similar sort of problem and was able to fit his data to a double Gaussian. But yeah, the data does definitely have a distribution to it. It's just not the one we expected. Any other questions? Yeah.
So I have a question about tooling. So one question is, would you happen to have some advice or guidance for continuous performance management? So something that basically tracks your performance every time you commit new code base to the version control system, particularly statistically valid, because I think you made an excellent point that we really want to care about the uncertainty of the measurement that we have.
The question was, is there a continuous testing framework that will do performance tests and that has all the machinery for doing everything and gathering the statistics you want? I haven't really found one that does what I want. I sort of have this collection of GNU plot and Python infrastructure that I've been working on, and I keep thinking I should really just rewrite it all in Python and create something like this. I don't know that there's a really good solution out there right now. I think the stuff that Mozilla does is pretty good, but I suspect that it's probably pretty tied to their use case, and I'm not sure if it's general purpose enough. I think it's probably very tied to their continuous integration system. I believe any system like this to be effective would have to be able to be tied into whatever continuous integration you're already using.
And one other tooling question. So I wonder if you found any use for the tools that come from the hardware research. So particularly what I'm thinking of is computer architecture research group at Carnegie Mellon University. So they have produced this tool. It has been just released this year. It's C++11 Remulator. And what it does, it's a cycle exact DRAM emulator. So for things like hardware jitter, and that actually be nice because it's a very precise model.
So the question was about simulators that simulate things like hardware jitter and do cycle accurate simulation. The answer is I work with a group of 6 people at Berkeley Lab. 3 of them are software guys. The other 3 do exactly what you just described. So the people who I do co-design with, I just started at the group that I'm at, but they have frameworks like this. We have we have one simulator that's at Berkeley Lab, and then there's this bigger simulation framework called SST that's at Sandia, which is the big one that gets used for a lot of HPC noise studies and HPC jitter studies.
Is it available as open source somewhere?
I don't think you can get. You might be able to get access to parts of SST, but we don't have the code, so it is Sandia. Yeah. Any other questions? Yeah.
You mentioned in one of your slides, but when you were transitioning your code to C++11, you started looking at the number of moves compared to copies.
Yeah.
And you created a unit test, but it wasn't clear to me. So, how were you looking at the number of moves?
So what we did was we created a mock object, and the mock objects would, whenever their move constructor or assignment operator would be called, they would increment a count, and whenever the copy constructor or copy assignment operator would be called, and whenever one of the relevant operators would be called, it would increment a count, and we'd pass it through the framework, and then we would go and pick it up afterwards, and we would look at what the counts were. And we would know sort of, if we're passing this, basically it was like we would take one of these mock objects and we would pass it in as an argument to async. And with async, because async is going to go do something asynchronously, you got to copy the argument in even if you can move it, because it may not be around when the async gets executed, but you should only have to copy it once. So we would just go through and look at the counts, and at first it would copy it like 6 times. And eventually, because we had many layers of our system, and eventually we worked on reducing those and adding in move semantics wherever we needed to within our framework to make sure that we were only copying once when we thought that was the guarantee that the interface should make.
This is specific to this particular code path.
Yeah, but I mean, I think generally, like, if you have an interface that takes something by move values, you should, if you take a generic type by move values in your interface, you should be thinking about, okay, somebody can pass in whatever data structure they want because it's just a templated parameter. How many times do I want to, what guarantees am I making about how many times I'm going to copy this thing, potentially? That if I'm taking it in by move, am I going to actually go and copy it at some point down the line?
Use SNE forward.
Yeah, you can do that, but we had a case where we wanted to move it a lot, if possible, but then once we got it to a certain point, we needed to make one copy. This may be something that's very tied to sort of an asynchronous interface where you've got to make the one copy, but we needed to forward it through the interfaces. But it ended up being really important for us. All right, any other questions?
So on your slides on stats, confidence interval, for example, a lot of that's based on central limit theorem. But I didn't really hear you talk a lot about n.
About?
The n that you use, the minimum n that you use. Do you find practically that 25 is really
what we tend to do is we tend to do a pilot group, and then we do more. So there's some math that you can do if you've taken some pilot points. You can go and figure out how large your sample size needs to be. That's normally the approach we take. The sample sizes that we tend to end up using tend to be 100, 200, maybe more. It really sort of depends, but if we're doing confidence intervals properly, we generally have to take a lot of sample sizes. I've had stuff where it's told me I need to go do 400 sample sizes, and I knew that was going to take me 2 weeks to do because I had to go run it because it was not something that ran quickly. But we do try to do that. So some of the graphs I've shown may have been at smaller sample sizes because it was just a pilot group. Yep.
I had a question and kind of a comment. So in your presentation, you made a distinction between calculating the variance and standard deviation on a sample versus a population. And my question and comment was, isn't that true also of establishing a distribution? Because the normal distribution, if I remember, only applies if you know the population, but you can do other distribution measures on sample sizes as well, correct? So you can do like the t-distribution.
Right.
More information about the outliers, because if you only do a normal distribution, your outlier from the mean, you may have false assumptions like, oh, this value came and it's this likely, but really it might be less likely.
The point is that I think the gist of your question is that if we're only looking at a normal distribution, we are potentially missing out in that you may want to be looking at other distributions, like a t-distribution. Is that
Yeah.
Yeah, so the answer is yes, but so one of the things, so early on I sort of mentioned that one of the things you want to do with statistics is you need to know both when to be really rigorous and when to not be really rigorous. We have done that in the past, but so much of our data for what we look at ends up being in a normal distribution that normally that's sufficient. We do end up going down that path, but we don't want to do so much statistics that it like prevents us from being able to get it done in a relatively quick time. Because, I mean, to some degree it's because our publishing requirements, we're already way ahead of what a lot of I think, people do frequently in CS. So the answer is yes, you're completely right. This is one of the places, I didn't want to get into other distributions too much here as well. Question in the far back.
Have you tried pinning like cache misses or prefetch misses as well, just beyond CPU time and stuff like that to try to find kind of like low-level regression and stuff that sort of modify the loop, but also like there's an increase in L of cache misses and that implies higher level tiny deviations?
So I'm sorry, can you restate that a little bit? Are you talking about whether we look at, you're going to have to rephrase that a little bit. I'm not sure the.
In your automated performance tests, do you also look at like low-level statistics like L1 cache misses or prefetch misses?
Gotcha. So the question is in on these automated performance tests, would we look at things like L1 cache misses or any of these low-level metrics, the sort of stuff that I'd look at in VTune? The answer is I'd like to sort of make more progress on just getting the main performance benchmarks automated, and then maybe start looking at stuff like that. Those are sort of auxiliary metrics in a way. If your benchmark's primarily looking at your L2 cache miss, then that's what I care about. But I think sort of baby steps first to get this sort of stuff implemented. All right, any other questions? We're running a little low on time, and I want to get out of here, so maybe one or two more. If there's any other ones. Nope. Okay.